The concept of neural networks is based on the structure and function of the human brain. The idea of using mathematical models to simulate the behavior of the brain can be traced back to the work of Warren McCulloch and Walter Pitts in the 1940s. They proposed a model of a neuron that could be represented by a simple mathematical formula. In the 1950s and 1960s, researchers such as Frank Rosenblatt and Marvin Minsky began developing more complex neural network models, including the perceptron, which is a simple feed-forward neural network that can learn to classify inputs into different categories. However, early neural network models were limited by the available computing power and the lack of large datasets for training and testing. In the 1980s and 1990s, advances in computing technology and the availability of large datasets allowed neural networks to become more powerful and widely used. The development of backpropagation algorithms, which allow the network to adjust the strength of its connections based on the error between its predicted output and the actual output, was a key breakthrough in making neural networks more effective. Since then, neural networks have continued to evolve and improve, with new architectures and training methods being developed to solve a wide range of complex problems in fields such as computer vision, natural language processing, and robotics. A neural network is a type of machine learning algorithm that is designed to mimic the way the human brain works. It consists of layers of interconnected nodes, or neurons, that process and transmit information. Each neuron receives input from multiple other neurons and applies a mathematical function to that input to produce an output, which is then passed on to other neurons in the next layer. Neural networks can be trained to recognize patterns and relationships in data, allowing them to perform tasks such as image recognition, natural language processing, and prediction. Training a neural network involves adjusting the strength of the connections between neurons through a process known as backpropagation, which involves minimizing the error between the network's predicted output and the actual output. Neural networks are a powerful and flexible tool for solving complex problems in fields such as computer vision, speech recognition, and natural language processing. They have been used to develop a wide range of applications, from self-driving cars to language translation software. Neural networks can be used in a wide range of applications across many different fields. Here are some examples of where neural networks are currently being used. Computer vision. Neural networks are used for tasks such as object detection, image segmentation, and face recognition. Applications include self-driving cars, security systems, and medical imaging. Natural language processing. Neural networks are used for tasks such as language translation, sentiment analysis, and speech recognition. Applications include virtual assistants, chatbots, and language learning software. Robotics. Neural networks are used for tasks such as motion planning, grasping, and manipulation. Applications include industrial automation, warehouse logistics, and assistive robotics. Finance. Neural networks are used for tasks such as fraud detection, risk management, and portfolio optimization. Applications include credit scoring, insurance underwriting, and algorithmic trading. Healthcare. Neural networks are used for tasks such as disease diagnosis, drug discovery, and medical image analysis. Applications include personalized medicine, clinical decision support, and remote patient monitoring. In general, neural networks are well suited for tasks that involve pattern recognition, classification, and prediction, particularly when the data is complex or ambiguous. As computing power and data availability continue to increase, neural networks are likely to become even more widespread in their applications. Advantages of neural networks: can learn from and adapt to new data. Neural networks can be trained to recognize patterns and relationships in data, and they can adapt to new data without the need for explicit programming. High accuracy. Neural networks can achieve high accuracy on tasks such as image recognition, speech recognition, and natural language processing. Ability to handle complex data. Neural networks can handle data that is complex, noisy, and ambiguous, making them well suited for tasks such as computer vision and natural language processing. Parallel processing: neural networks can process multiple inputs simultaneously, which makes them more efficient than traditional algorithms for certain tasks. Fault tolerance: neural networks can continue to function even if some of their components fail, which makes them more robust than traditional algorithms. Disadvantages of neural networks. Need for large datasets: neural networks require large datasets for training and testing, which can be difficult and expensive to obtain. Computationally intensive: neural networks can be computationally intensive, particularly for large datasets and complex architectures. Black box nature: neural networks can be difficult to interpret and understand, particularly for complex architectures. This can be a disadvantage in some applications where transparency and interpretability are important. Overfitting: neural networks can overfit to the training data, meaning that they perform well on the training data but poorly on new data. Need for expertise: neural networks require expertise in machine learning and data science to design, train, and evaluate effectively.